computer's ahead of me, so welcome to the Stuffler Broadcasting Studio again. We're going to do a slideshow on probability. And probability, unfortunately, this is kind of going to be long. There's quite a few slides I want to go through. And there's various topics that need to be covered in probability. And probability probably is the most difficult of the first 4 chapters in your text. I'm going to ask you to try not to get too bogged down in some of the complexities that you might see, and I'll try to stress what is the most important for you to know. Anyway, we got quite a list of topics here, so we might as well start. And the best way to start when you're doing probability is with the birthday problem. So here's the problem. If you and I were to walk into a room with 50 people, what is the probability that 2 people will have the same birthday? Now, we're logical, rational people. So do you think that probability would be rare, that it would be a low probability, or do you think it'd be more common and that it would be a high probability? Well, the reality is, the answer is there is a 97% chance that at least 2 people in a room out of 50 persons will have the same birthday. So sometimes probability can be maybe fool us a bit and maybe not be quite as logical as we might think. So let me get us started with this particular problem. And one thing I wanted to caution you about is that as you go through probability applications, sometimes there's 2 ways to do a problem. There's an easier approach, and then there's a more difficult one. So I'm going to see if you can help me on this one. Which do you think would be easier? Do you think it would be easier to determine the probability that at least 2 people have the same birthday, or the probability that no one has the same birthday? Well, I hope you picked the second choice, and we're going to do that. That would be easier, the probability that no one has the same birthday. And mathematically, the way this works is, well, the first one is 366 out of 366 days. The second one would be 365 out of 366 days, times the third one, which would be 364 out of 366 days. And you would keep doing that till you got to the probability of 317th out of 366 days. So the probability of no one sharing a birthday mathematically works out to about 3%. So if nobody's sharing a birthday in those 50 people that are in the room is 3%, that means that the probability of at least 2 sharing a birthday must be 1 minus that, or the 97% that I've already referred to. Okay, so there's some terms that you need to get used to and comfortable with. First of all, there's something called the sample space. The sample space is all the possible outcomes for an experiment. And all these experiments that we refer to are random experiments. What we mean by random is that we don't know the results in advance. For example, if I were to toss a coin, you and I both know I could either get a head or a tail. But we don't know which I'll get, so we don't know the results in advance. We can move on now. Of course, when you get to probability, we always think of gambling, and the reason we think of gambling is because it goes back to the 1700s and a mathematician, a Frenchman, who was interested about probability and gambling. But let's go to the example of rolling a dice, or a single die. The sample space, as S, the possible outcomes would be 6. We could roll a 1, a 2, a 3, a 4, a 5, or a 6. What's the probability of rolling a 2? 1 out of 6. A 5, 1 out of 6. But when 2 dice are rolled, the sample space becomes a lot bigger. And here's what it would look like. It's 36 distinctive outcomes. So, an event, that's another word you need to get familiar with. An event just means an outcome in the sample space. And if we're talking about rolling 2 die, we could talk about a compound event. And a compound event could be rolling a 7 on the roll of 2 dice. And that could be 6 possible different ways we could roll a 7. We could roll a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, or a 6 and a 1. So where it says ice there, it should say dice. But anyway, there are 6 different ways to roll a 7 when we roll 2 die, or 2 dice. So that means that the probability of rolling a 7 is, well, what is it? 6 out of 36. Now, probability, this topic probability. First of all, the probability of any given event occurring basically is just telling you the likelihood that that event will occur. Probability is measured from 0 to 1 inclusive, meaning the probability of any given event must lie within that interval from 0 up to and including 1. If probability event is 0, then that means that event won't occur or can't occur. If the probability is equal to 1, then of course that event will occur. It's a certainty. And so probability is usually stated in decimal form, not fractional form, but decimal form. So the probabilities of all simple events has to equal 1, meaning the probability of rolling a 1 plus the probability of rolling a 2, 3, 4, 5, or 6 on a single die has to add up to 1. And I've given you a way that we can arrive or assign probabilities in this example of, say, customer purchases. So let's say that for a particular store, they found 32% of the purchases are paid for by credit card, 20% by debit card, 35% cash, and 18% check. We can turn that into probabilities by just turning those into decimals. This column adds up to 100%, and this column adds up to 1. Now, the law of large numbers is an important element to this subject of probability. We always prefer a large sample to a small one. If, for example, we were to flip a coin 50 times, we would expect about half, or 25 heads. So the probability of head would be 0.5. Now, if I flipped a coin 10 times, would I get exactly 5 heads? Probably not. I might get 6, I might get 4, I might get 7. And how many different possible outcomes would there be if I tossed a coin 10 times? Be 10 different outcomes. I could have anywhere from 1 head to, actually, 1 head to 10 head. There's actually 11 outcomes. Could I toss a coin 10 times and not get any heads? Absolutely. I could get from 0 to 10 heads. So typically when we're doing an experiment, we're going to need a larger n, a larger number in the sample to get close to that particular 0.5 if we were tossing a coin. Now, there are certain bases for probability. One of those bases or approaches that we use is something called classical approach, which is based on logic. And basically, when we're talking about the classical approach, we're talking about equally likely outcomes. We don't perform the experiment, but we rely on our deductive reasoning to determine probability. And when we don't perform the experiment, what we're actually doing is a priori, we're assigning probabilities before the event is observed. So a priori probabilities, again, they're assigned before the event or before we do the experiment. They're based on logic, not experience. And we can give an example of the classical approach for the 2 dice experiment. We can figure out the sample space, all 36 possible outcomes, and then from that sample space, without doing the dice tossing, we can find those outcomes where we get a 7. And all we do is do the probability by calculating the number of outcomes with 7, which is 6 of them, divided by the total number of outcomes, 36, and that tells us that the probability of rolling a 7 or getting a 7 on 2 die is 0.1667. 6 out of 36, 1/6, or 0.1667. Then there's a subjective approach. We could say it's someone's personal belief about the likelihood of an event. And you know, often this likelihood or belief comes from experience or based on data that comes from, you know, past history. And here's a couple examples of the subjective approach to probability. What is the probability that a new truck product program will show a return on investment of at least 10%? Well, let's say that GM wants to come out with a new truck and they research what has happened when new trucks have been offered for sale in the market in the past. They know what their costs of production are. They know they've got to have a specific rate of return on their investment to make it worth it. So that probability is something that they can estimate. It will be somebody's personal belief, but it will be an educated guess based on past data. What is the probability that the price of Apple stock will rise within the next 30 days? Do we know that outcome? Absolutely not. We don't know because there's so many different factors, but we can look at trends and other information that will help us determine what the likelihood that Apple stock will rise within the next 30 days might be. Now, there's a lot of rules of probability and just some information that you need to get a little bit comfortable with. In your textbook, I'm sure you have what are called Venn diagrams. And a Venn diagram is just this rectangle, and it contains the sample space. And in this particular Venn diagram, there is this event A, and then there's this event outside, which is not A. So we denote it by A prime, or sometimes the textbooks will put a bar over the A to suggest that it's not the event A, it's the complement. It's everything but A. If A is the probability or the event of having rain, then the complement would be the event of not having rain. So the probability of rain, A, plus the probability of not rain has to equal 1. So that means if we know that the probability of A is 0.3 for one day, then the probability of not having rain has to be 1 minus 0.3. There are some words that you're going to have to get used to. I confuse them all the time, so if you do, don't feel alone. It's just kind of the nature of the beast. So there is something called the union. Union. When you see the word union, think or. A or B. So we've got two events. Here's event A, and here's event B. When we're talking about the union, we want to know the probability of A occurring or B occurring or both occurring. And so that would be this area here. And anything outside of it, it's not A or B. Again, union, A or B. Again, it's denoted with this union sign. Think of it as or, and it means one or the other or both events may occur. And that's contrasted with the intersection. The intersection is both events occur simultaneously, A and B, the probability of A and B. So intersection is denoted with this upside down U symbol. Intersection, think and. They both occur. Both A and both B occur. So we're talking about just this region in the Venn diagram. And it's also referred to as what is called a joint probability, meaning you got A occurring and B occurring simultaneously. Okay. Now, part of these rules of probability, there's the first one is the general law of addition. It says the probability of the union of two events. The probability of A or B. The probability of A or B is the probability of A plus the probability of B minus the probability of both. And let me show you a diagram to help clarify that. If we want to know the union, the probability of A or B or both, then we add this probability to this probability, but we're counting this center section twice. We're counting the intersection twice, so we have to subtract that out. So in order to determine the probability of A or B, we have to take the probability of A plus the probability of B minus the probability of A and B. So let me give a few examples here just with standard decks of cards. Okay, first of all, here's my Venn diagram. And I'm going to have this event Q being drawing a queen. And if you know anything about playing cards, a 52 card playing deck, then you know that there's 4 queens in the deck. So the probability of drawing a queen is 4 out of 52. The probability of drawing a red card, well, a red card is this probability, and there's 26 red cards in a deck of 52. So the probability of drawing a red card is 26 out of 52. And then we're asked, what's the probability of both a queen and a red card? Well, that's this region here. And if you know anything about a deck of cards, we've got 4 queens. Half of those 4 queens are red, half of them are black. So the probability of drawing a queen and a red card is 2 out of 52. So here we're asked the probability of a queen or red card. So we're asking about all of this, but then again we've got this intersection in there twice, so we've got to subtract it out. So the probability of drawing a queen or a red card is equal to the probability of queen plus the probability of a red card minus the intersection minus the probability of both. So that comes out, probability of a queen 4 over 52 plus the probability of red card 26 over 52 minus the probability of both. And if you do the math, that works out to 0.5385, or there's a 53.85% chance of drawing a queen or a red card. Some of the other terminology that you need to get comfortable with is something. The first phrase here is mutually exclusive. And for mutually exclusive events, I've given you the technical definition up here, but mutually exclusive events don't share any elements, meaning they are completely separate. The event A can occur, B cannot. Or the event B can occur, A cannot. They don't share any elements. So if we want to know the probability of A and B when they're mutually exclusive, then you just do a straight addition. Probability of A and B is probability of A or B is equal to the probability of A plus the probability of B. Now if I had to make like an example for this, well, I think I'm going to skip it. I'm going to go on because I know I've got a long set of slides here. Another phrase or term that relates to probability is that events can be completely exhaustive if they're two event A and B occupy the entire sample space. For example, a car can either be covered by a warranty or it's not. You need your car repaired, you either have a warranty or you don't have a warranty. That's exhaustive. There's no other possibilities. Okay, there's another type of probability called conditional probability. You'll see problems that are stated that given that A has occurred, what is the probability of B occurring? And the way it's denoted, in this case, the probability of A given B has occurred. This line is just read given. So the probability of A given B has occurred Here's the formula for it. But again, I don't want you to get bogged down in formulas. One thing I want to stress in this class is please do not be spending a lot of time looking at formulas. We're using a software that does calculations for us. While it won't do probability calculations, such as being examined in Chapter 4, it's more the concept that is important. So concept, concept, concept. So what this basically says, this formula, is that given B becomes 100%. And we want to know what part of that, what proportion does the event A and B represent of just B. So another way to show that, is to go to the next slide. Consider the logic by looking at this diagram. Okay, the probability of A given B has occurred. Here's B. Ignore A. Just don't look at this. It's not there. Here's B. We're only concerned with B. So, given that B has occurred, what is the probability of A? Well, this is the probability of A. A represents this portion of B. So to calculate the probability of A given B, you take this probability divided by the probability of B. So it's really like a ratio of this part of the circle to the entire circle. But again, you forget the rest of A. So let's use an example here. Let's say we're talking about high school dropouts. And let's just say for this data that this represents the population aged 16 to 21 who are not attending college. Well, 13.5% are unemployed, 29.05% are high school dropouts, and 5.32% are unemployed high school dropouts. And this is of the population that is aged 16 to 21 and not in college. So the question is, what is the conditional probability that a member of this population is unemployed given that they're a high school dropout? Well, given that they're a high school dropout, that's what we want to look at first. Here's the high school dropouts, 29.05%. And what is the probability that they're unemployed? Well, here's the probability of being unemployed. So, if you use U as being the event that the person's unemployed, D that they're a dropout, then I've given you the two probabilities. The probability of being unemployed is 13.1350. The probability of being a dropout is 0.2905. And that's straight from the table. I just took the percentages and turned them into decimals. So the probability of being both, well, that was that third item on the table. The probability of being unemployed and a dropout was 0.0532. Let me return to that slide just for a minute so that you can see where I got these three numbers. Okay, probability of unemployed, probability of a dropout, probability of both unemployed and a dropout. Okay, again the question is, given that a person is a high school dropout, what is the probability that they are unemployed? So the probability that given they're a dropout, they're unemployed is the probability that they're both unemployed and a dropout. What proportion is that of being a dropout? So 0.0532 divided by 2905, and we get a probability of 0.1830, or 18.31%, which means that given a person is a dropout, the probability that they are unemployed is 18.31%. And if you notice, the probability of being just unemployed was 0.1350. So why am I telling you that? Well, because being a high school dropout is related then to being unemployed. Independent events. Now, two events are independent if the result of the second event is not affected by the result of the first event. Essentially, that another way to say that is, if one event occurs, it has no effect on whether the second event will occur or not occur. So, returning to our unemployed and dropout example, again, the probability that given somebody's a dropout and they're unemployed came out to be 0.1831. That is greater than the probability of being unemployed, which was 0.1350. So, the probability of being unemployed and the probability of being a dropout are not independent. They're dependent. And so, if you're a dropout, then it certainly will have an effect on whether you may or may not be unemployed. They're dependent variables. They're not independent. There's another way to check for independence, and I'm going to just skip that because I'm sure that's in your book and you can see the math. And then these two slides talk about odds. The odds in favor of an event occurring, these would be the way you calculate odds. I'm skipping that. Then that would be the odds against event A occurring. So in case you're interested in how odds are calculated, or if you want to know odds in favor or odds against an event, then you have this slide to refer to. I'm not sure if your book covers that or not. Again, this is still relating to the odds and probability. Okay. There is a multiplicative law or a multiplication law for the probability of independent events. Remember, the probability of event A has no effect or no impact on the occurrence or non-occurrence of B. When that's true, then to calculate the probability of A and B, or A1 and A2 and N, all the way to A sub N occurring, or the last event, is just to multiply those probabilities. But it's easier to kind of do an example, so let me show you an example. Suppose a website has two independent file servers. Each server has 99% reliability. What is the total system reliability? First of all, we're going to do one of those easier problems, and we're going to define event F1 to be the event that server 1 fails. F2 is going to be the event that server 2 fails. Now, these are independent events because if the first server fails, that has no impact on whether the second server will fail or not. They're independent. So in order to calculate that probability, the probability of the first server failing and the second server failing would be the probability of the first server failing times the probability of the second server failing. And since they've got a 99% reliability rating, then the probability of failure on 1 is 0.1. The probability of failure of 2, the second server, is 0.01. Multiply those together, and you get the probability of both server 1 and server 2 failing as being 0.001. So that means the probability that both servers are down is 0.0001. So the probability that at least one server is up or running, or reliability, is 1 minus the probability that they both fail, or 99.99%. So you can be certain with 99.99% level of certainty that both servers will, at least one server will be up and that website will continue to operate. Okay, now here's a contingency table, and let me refer to this and just give you a little bit of time to look at it. This particular example shows MBA programs, 67 of them. across the United States. And it rates these programs by their tuition. A low tuition is T1, meaning that it's under $40,000 a year. A medium tuition from $40,000 to $50,000 a year tuition, and a high tuition would be greater than $50,000. So these are the tuitions. You can see that there are 16 institutions out of the 67 that have a low tuition. A medium tuition would be 19. A high tuition would be 32, so like about half charge a high tuition. And then, well, we want to rate that against salary gains. If you're going to this MBA program and you're paying low, medium, or high tuition, you want to know what your rate of return is going to be. So in this case, a small salary gain, meaning under $50,000 a year, was estimated from these various tuition levels, these different institutions. So 17 of the 67 had small salary gains. Then there were the medium salary gains from $50,000 to $100,000, and that was 33 institutions that whose graduates had a medium salary gain from $500 to $100,000. So 33 out of 67. And then large salary, meaning a gain of more than $100,000. Well, there weren't many. There were only 17 out of the 67. And as you can tell from this table, well, the lowest tuition institution only had one gain of over 100,000 or 100,000 or more, and the medium had one gain and of over 100,000, but the highest tuition institution had 15 students or 15 graduates that earned over 100,000 in additional salary. So we can turn this contingency table, and that's what it's called, into some probability applications. So let me go to the next slide. Are large salary gains more likely to accrue to graduates of high tuition MBA programs? So again, let's return. Large salary gains, are they likely to accrue to large tuition programs? Yeah. Here's the largest salary gains. And the 15 were all from high tuition institutions. So the answer is yes. So the frequencies indicate that MBA graduates of high tuition schools do tend to have large salary gains. Also, most of the top tier schools charge a high tuition. So that's, again, you can see that from the data. But let's do an example. And the example here I'd like to ask is, what is the probability of a medium salary gain? Probability of a medium salary gain, and let me go back to that table. So looking at this table, what do you suppose the probability of a medium salary gain is? In that case, you're just taking 33 out of 67. So 33 graduates out of 67 had a medium salary gain. Which would be 0.4925, or 49.25% of the graduates had a medium salary gain. So you could also state that we can conclude that about 49% of the salary gains at the top tier schools were between $50,000 and $100,000. That was that medium gain category. What is the probability of a low tuition? Okay, so let me go back to that table again. Whoops. Probability of a low tuition. Well, here's my low tuition. And there were 16 graduates that paid a low tuition out of 67. So the probability of a low tuition, 16 out of 67. And let me go forward again. Oops, I had the table right there and didn't realize it. 16 out of 67, probability of a low tuition, which comes out to be 0.2388. So there's a 24% chance that a top-tier school's MBA tuition is under $40,000 a year. Okay, so when we're calculating probability using row and or column totals, what we're talking about or what we're using are called marginal probabilities. We did that twice in the two preceding examples. So again, this percentage, 16 out of 67 for the low tuition colleges or graduates, and then 33 out of 67 for the medium salary gain out of the 67 graduates. Those are both called marginal probabilities. But we can also do something called a joint probability. And the joint probability, in this case, I'm asking you, what is the joint probability that the school has low tuition and large salary gains? Low tuition and large salary gains. So I'm going to give you a moment to think about that. One out of 67. I hope you saw it on the table. So the probability of both a low tuition and a large salary gain was 1 out of 67. So there's less than a 2% chance that a top-tier school has both low tuition and large salary gains. So let me return to that last slide. And what you should have been looking at in the table for low tuition and large salary was this number right here. So obviously this is the most desirable. Lowest tuition, large salary gain, and the likelihood of that was 1 out of 67. So what was the likelihood of a high salary and a high tuition? That was be 15 out of 67. Okay, let me return to my slide. Okay, another probability question. Find the probability that the salary gains are small given that the MBA tuition is large. Well, that would be making me pretty unhappy. So it would be written the probability of a small gain, salary gain, given a small gain. Am I saying that right? Let me say. Yes, given a small salary gain that you went to a school and paid a high tuition. Oh, I thought I had that on this slide. Okay, let me go back. Sorry. Probability that given the salary gains are small and the tuition, what is the probability that tuition is large? Given that, I keep reversing it. Sorry. Let me start that again. Given that the tuition is large, I have this written wrong. Shoot. Okay. Ignore what I have written here because I've written it wrong. This reads, given that there is small gains, what is the probability that they went to a high tuition school? Let me go back to the table. Oops, missed it. Okay. Given that they went to, that their salary was, their gain was small. You know what? I'm getting myself confused by switching back and forth. So let me just skip that slide because I can't remember what it was. But I'll do it from just this looking at this table. Given that they had a small salary gain, we're talking about this column of the table. What is the probability that they paid a low tuition? 5 out of 17. What is the probability that given they had a small salary gain, they paid a medium tuition? That would be 7 out of 17. And again, given they had a small tuition or small salary gain, what is the probability they paid a high tuition? 5 out of 17. I don't think I'd be real happy if I were them. Okay, let me go back and find the slides where I left off. Okay, counting rules. Now, there are some counting rules that you need to become comfortable with. They are important. And in fact, let me also mention here that for probability, I think you should feel very comfortable working with a contingency table. regardless of what probability you might be asked, whether it's a marginal probability, a joint probability, meaning that it's given something. What is the probability of this occurring? You should be very comfortable with any probability that you might be asked about from a contingency table. You also need to be comfortable with the counting rules. And the first fundamental rule of counting is, as it tells you here, if event A can occur in n1 ways and event B can occur in n2 ways, then event A and B can occur in n1 times n2 ways. So a really very complex example of that is how many unique stock keeping units, you know, all those SKU numbers on things, can a hardware store create by using 2 letters ranging from AA to ZZ, followed by 4 numbers, 0 through 9. Well, that's taking 2 items and saying how many arrangements can we make from 2 items, meaning the letters and the numbers. And so that formula is you take 26 times 26, the first letter is going to have 26 possible ways, times the second letter, 26 possible ways, times 10 numbers, because these SKU numbers are going to be 4 numbers, 0 through 10, times 10, times 10, times 10. Well, it ends up that the fundamental counting rule is 6,760,000 different inventory labels or SKU numbers that a hardware store could create using 2 alphabetic letters and 4 numbers ranging from 0 through 9. Then there are factorials that give you the number of ways that n items can be arranged in a particular order. It's a factorial. The way factorials look is n with an exclamation point. And for example, if something can be arranged if you got 5 items and you want to know how many different ways they can be arranged, then it'd be 5 factorial. That would be 5 times 4 times 3 times 2 times 1. And that is how you calculate a factorial. And again, what you're doing, and when you use a factorial, is to count the possible number of arrangements of any n items, one group of items. So, as an example of a factorial, here's a problem. A home appliance service truck must make 3 stops, A, B, and C. Those 3 stops, we'll just call them A, B, and C. And how many ways could the 3 stops be arranged? Well, that's a simple factorial. 3 factorial times 2 times 1, and that tells you that you could arrange 3 stops. You could make 6 different arrangements of the 3 stops. And if you want to list those, we can do that. You can go ABC, ACB, BAC, etc. But that is the 6 possible arrangements of 3 different stops. Now, permutations. Well, permutations. You're always taking, this is the way it's designated, you're always taking a certain number of items, R, from a group of items, N. And you're finding out how many arrangements you can make in a particular order. So order counts. When you're talking about permutations, order counts. For example, how many ways can the R items be arranged, treating each arrangement as different? For example, is XYZ different from ZYX? Yeah, of course. That's a permutation. A combination. Well, a combination is an arrangement taking R items chosen from N items, and the order of the selection is not important. For example, XYZ is the same as ZYX. The combination is denoted NCR, meaning you're taking R items at a time from N total items and finding out how many combinations or arrangements when the order is not important. So let me go through some examples with you to see if you can figure out, is it a permutation, is it a combination, is it a factorial, or is it the fundamental counting rule? Okay, in this first problem, we're going to make a 5-person committee from 20 workers. How many different committees could we form of 5 people from 20 workers? Is that a permutation, a combination, a factorial, or is it the counting rules, the fundamental rule of counting? Well, it's not the fundamental rule of counting. It's not a factorial. If you were to take a committee of 5 people from 20 workers, and let's say you had person A, B, C, D, and E, would that be the same as B, A, C, D, and E? Yeah, it's the same committee. So does order count or not? Okay, a 5-person committee from 20 workers, that would be a combination, because the 5 same people, no matter in what order, are the same committee. Combination. How about you're going to take a president, a vice president, and a treasurer from 20 workers? Would that be a combination or a permutation? How many ways can you arrange president, vice president, and treasurer from 20 workers? That would be a permutation, because it would certainly be different if the president was A, the vice president was B, and the treasurer was C. And then if you did B, C, A, it's the same 3, but the order counts. B would be the president, C would be the vice president, and the treasurer would be A. So order counts, so that makes it a permutation. Okay, I have 25 books and 4 shelves. How many ways can I arrange the 25 books on the 4 shelves? That's the basic counting rule. 25 times 4, or 100 ways that I could arrange the 25 books on the 4 shelves. How many 4-letter arrangements can we make from A, B, C, and D? How many 4-letter arrangements can we make from A, B, C, and D? That's 4 factorial. You're using all of them and figuring out how many arrangements you can make. 4 factorial. Okay, let's say we want 4 tennis players from a team of 10. How many arrangements of 4 tennis players from a team of 10 can we do? Is that a permutation? A combination? We're taking 4 at a time from 10, so it has to be one of the 2. Is Ann, Bob, Joe, and Mary the same as Joe, Mary, Ann, and Bob? Yeah, they're the same team. So that means it's a combination. And then lastly, how about 3 numbers from 0 to 9 to open a lock? How many different arrangements of 3 numbers from 0 to 9 could we use to open a lock? Okay, we're taking 3 at a time from 9, 0 to 9. So we're taking 3 at a time from 10 numbers. That tells you it's not the counting rule. It's not a factorial. It has to be a permutation or a combination. And definitely 1, 2, 3 is different than 3, 2, 1. So that means it's a permutation. Every order counts. Okay, I hope that gives you a little bit of overview in Chapter 4. Try not to get too bogged down with Venn diagrams and the rules of probability, the formulas for probability. And concentrate, please, on the counting rules and also the contingency tables and determining probability from contingency tables. Good luck with Chapter 4.